Okay.
Welcome to the seminar of the IAU Commission, the Local Universe. And today we will hear a presentation by David Benisty from the Cambridge University. And for the first time, we will have a talk at our seminar about the dark energy. So you are welcome to present, David.
Thank you very much. Let me just open the door because I think the Wi-Fi will be better. Sorry about this. Okay. So, okay, sorry about this. Thank you very much for the invitation. And yeah, so I will speak about dark energy or how to constrain dark energy in the local universe, which seems to be something which is a bit surprising, but it's possible. And I mean, I'm going to give a bit motivation about two-body problem and also how to address the cosmological constant in two-body problem. And then you will see why actually in the local universe there is this kind of impact of dark energy. So let me just review shortly what we're referring to when you were saying dark energy. So I'm sorry, I'll try to close the bit. Okay, I'm sorry about it because the Wi-Fi is not complete. Okay, so here we can see a different signs of dark energy. So I mean, again, from all of these kind of systems, we have to go at least to distant galaxies or in the late universe or in the early universe, from the radiation of the Big Bang. And only from this kind of galaxies we can track the expansion rate. So it means, for instance, I mean, you can see in the upper plot, distance modulo versus the redshift. Again, I have to go in some distances where I can treat to my void on average as kind of uniformly expanding or contracted, something like that. I mean, that I have that the assumption of the cosmological principle is actually valid. And then I can see the expansion rate from different ratios. I mean, if I included dark energy inside or not. And as I guess that we all know that, for instance, you can see in the plot, if you can see also can you see my my mouse? I mean, can you see the
yes,
sign?
Yes.
Yes. So when I'm taking the omega matter to be 30% and the cosmological constant to be dominate, the ratio of the cosmological constant inside the universe in a certain rate, I get a very good fit for the distance modulo versus the redshift, which means that the universe is actually expanding and also accelerating. But if I'm not including the cosmological constant, obviously I get a different expansion rate. Okay, so this was in some way the first sign from 1998 about the cosmological constant, but also we have a lot of other data sets, which include from baryon acoustic oscillation. So it means from the power spectrum of galaxies in the sky, and also from the cosmic microwave background radiation. So it means that we have the map of the radiation in the early universe. And from the power spectrum that we can make on this kind of temperature, we get this very famous plot. Okay, this is the lower plot. And if I run this fit for different ratios, it means that I run this only with matter, universe only with matter, or matter and dark energy in the proper ratio, I'm getting a very nice fit. So this is why we see also from the late universe and also from the early universe signatures of this dark energy. Okay, I mean, I think now this is up to now it's something which is mostly familiar for all of us. It is possible to mimic the dark energy by other models, but I mean, I'll just skip about this thing because this is more a theoretical aspect or to do modified gravity. But let's now skip about these external models. And now let me show you in a second how can we detect or constrain dark energy from a nearby galaxy, and actually why. There is a fundamental reason that I'll show in a second, why Andromeda galaxy is very sensitive to the cosmological constant value, and why other galaxies, they are not sensitive to that. Why the solar system, for instance, is not sensitive. Okay, so I'll show like in a second this condition. So first of all, before we go like to the local group, let me just like describe to you like a very simple model. This very simple model I have like to fix by simulations, but I mean, this is kind of like the first model, the first approach that we use in order like to model the local group of galaxies. So in this kind of approach, what's called the timing argument, it means that we're assuming that the Milky Way and Andromeda, there are two separated galaxies, kind of like two isolated bodies. We know from the measurements what are the separation and the velocities of Andromeda. And most of the history of the universe, they're not like interacting so much. Is this assumption is correct? Most probably for most of the history of the universe is correct, but we have like to go to simulations like to modify, you know, like to correct like all of these kind of ratios that we get. But this is kind of like a very simplistic approach. Okay, so this is kind of like the model of the local group that we're like as a simple assumption taking local. You can stop me any second for any questions, please. So, also, the properties of Andromeda, I mean, like all of the dynamics, the velocities and the separation, they are known. So, I mean, we have like different estimations. So we have also the separation, which is about like 1 megaparsec, and we have the radial and the tangential velocity. Now, the radial in the tangential velocity, they are not like in why the main reason I show like this number is also like to tell us this is not in the post-Newtonian regime. So it's fully Newtonian. I don't have like to take any post-Newtonian, like for instance, like the pulsars or something like this, where the velocities are higher. Okay, so I mean, it's fully Newtonian in that sense. So speed of light is much, much higher. Yes. So, and you can see also like from different estimations in the literature about the tangential velocity, it's like a big issue. In earlier times, it was like about up to 17 kilometers per second. After, like in this reference in 2015, London 2015, it was like about 50. And more recent publication, it was like about 80 with very big error bars. Now, the recent publication, this is kind of like a different method from the dynamics using by Gaia. But I mean, you can see that we have like different estimations of the tangential velocity. So I have like to take all of these kind of different estimations into account. Okay, but all of them are fully in the fully Newtonian regime. Any questions so far? Okay. So in our assumption, so I mean, in our very simplistic assumption, what we call like the timing argument, we're assuming that we know currently today the location of Andromeda, okay, the separation, and we assume that initially they started like in a very small separation. What's called like the Big Bang. I mean, it means like that initially they start like in zero. Okay, not practically zero, but very close like to zero. And because you had like the final condition, you have like the final point, and you have also the initial point, you can extract the mass from this kind of like motion. Okay, so how can I do it? So, 1 second. So I'm using actually the Newtonian equation of motion, r double dot equals to gm over r square, but also I have the contribution from the tangential velocity. So this is kind of like the angular momentum. Okay. Now I'm also adding the cosmological constant inside. Now, let me give you just kind of like an intuition why I have to use the cosmological constant in order to get the mass of Andromeda, for instance. So if we only take, you know, just kind of like hand waving, I would say. If I'm going to take the mass 10 to the power of 12 solar masses, which is more or less the mass of Andromeda and Milky Way, the mass of the local group, and the separation is about 1 megaparsec, okay? So this kind of acceleration that I get is actually canceled by the acceleration that we get from lambda, from the cosmological constant, surprisingly. So it means I cannot ignore in this regime by the repulsion force of the cosmological constant. Now, this kind of like hand waving, because I told you, let's put like more or less the mass, let's put more or less like the separation, and then I can show that these two forces are canceling each other. There is a fundamental reason that I'll show you like in a second, that you will understand why in Andromeda is sensitive to the presence of lambda. Okay, in a second I'll show that. So, I mean, here you can see, this is kind of like the effective potential of Milky Way and Andromeda. So, I mean, here you see when I put like the potential without the cosmological constant, and when I include the cosmological constant inside, so the curve changed like to the blue curve. Andromeda is more or less here, okay, like in this location. So it means it's very, very close to the point where it's going like to run away to infinity. If Andromeda was a bit further, the lambda r force would be stronger than the Newtonian one, and then it would try like to run away to infinity. Okay, so as I told you before, we have the final condition, we have like the separation, the phase space, the final point, and we assume that also like they started like in the initial point very close to each other, and then numerically we can calculate the mass of Milky Way and Andromeda. Okay, and this reference by Petrich and Lahav and Hoffman, I think they're not like the original, because there is like a few references by before, but I mean, I think they made it as a very nice strong statement. They showed that if you include the cosmological constant by the timing arguments, so it means you assume that they were separated like most of the history of the universe, the mass of the local group is increasing by 10%, which is a very surprising result. Okay. Any questions so far? Okay.
So do you mean that if there was no cosmological constant, the two galaxies should have interacted so much more? No?
If the two galaxies, if you don't have like any cosmological constant, the mass is going to be like about 4. And if you include the cosmological constant, is increasing to 4.5, because you have like more repulsion force, because like the cosmological constant is caused like to the galaxies like to run away. And then you need like more mass in order to finish in the same separation and velocities that you measure today.
Okay.
Okay, so that's all. I mean, and again, this is not like how we are really going to estimate the mass, because we're using also like simulations, like pairs of galaxies. But this is only to show, okay, I have to take lambda into account in this system. It's not negligible. Okay. Any more questions? Okay. So I wanted just like to get some intuition why actually in Andromeda is so sensitive to the cosmological constant. Now, I'm going to skip like all of these kind of like equations, but I want to show you this dimensionless parameter. Can I try? I want like to write on the board that I have, because I think this is going to be much more clear. Let me see if I can do that. Yes. I want now to give you kind of like a very simple derivation, okay? And let me say that all of the derivation that I've done, also like analytically or also like numerically, is based on this one. But I mean, there is a very simple derivation that you can see, that you can find like the condition. So we have like, this is the acceleration, as we all know. This is the Newtonian force, okay? And this is the cosmological constant contribution, the repulsion force of the cosmological constant. Now, I wanted like to define this dimensionless parameter, which quantifies for me how much this part is going to be dominate over the Newtonian part. So it's only like the ratio in between lambda c square r and the Newtonian force, okay? So let's write it down over gm over r square, okay? So again, this kind of like dimensionless parameter quantifies for me how much lambda is going to be dominate. Now I can take like the r to the denominator, right? So it's going to be lambda c square over gm over r cube. Now let me just ask you, what is gm over r cube in binary motion? Gm over r cube is the period, omega square. So you see that I have kind of like very important period, which is come from the cosmological constant. I can call this omega lambda. And I have the Keplerian period on the numerator. I can rewrite this term as T Keplerian over T lambda. So it's going to be like 2 pi over this. Now, this T lambda, if I'm taking like the value from Planck, it's going to be more or less 63 gigayears. This T lambda from Planck is 63. And the Keplerian period of Milky Way and Andromeda, I calculated it because I have like the final conditions and so on, is about 17 gigayears. So 17 over 63, this is kind of like 5 times more, no, 3 times more, okay? So, I mean, this square is about like 10%. So this is actually the fundamental reason, because like this parameter that you see, lambda, was always repeated in the solutions that I found, like the two-body problem with lambda, with cosmological constant. And always this kind of like small lambda appeared in the solution repeatedly. So I know, and this is kind of like now you can have like, you can take this with yourself as a statement, as a general statement. If you have a binary motion of two galaxies, okay, 1 second, let's go back to the slides. Here, you see like the derivation that I've done. So this is kind of like, instead of R, I put like the semi-major axis, okay? But this is the T Keplerian over 63. The period of Milky Way and Andromeda is 17. So this is kind of like a general rule. If you have any binary motion, binary stars, binary galaxies, if the period of this system is going to be large, in the sense of like the edge of the universe or even higher, very close to 63, then the cosmological constant is going to perturb the whole binary motion. Okay, this is kind of like the key condition. Okay, now I put like in this plot different like systems, because I wanted like to see, okay, the phase space, or like to see different systems, how they affected. So the local group, I mean here on black, I put like the 63. This is kind of the value from the cosmological constant. On blue, I put the edge of the universe, 30.7. And here, this is the period of Milky Way and Andromeda, about 17. So this is why this system is sensitive to the cosmological constant. Now, in a comparison, you can see like other system, like the S2, this is kind of like the stars around the galactic center. You have binary pulsars, which are pretty frequent, okay? Or Mercury, okay? And all of these stars, the period much, much lower. So this is why, I mean, from the theoretical solution, you see here, this is kind of like the solution that I found, okay? You can derive it. But you can see that the condition is always related to the period of the system. So the statement that I want to also like to tell, the cosmological constant, we always think about this as a scale of length, critical length, like the size of the observed universe. But if you solve the two-body problem, it's actually a critical period. And because of this kind of like about 60, Milky Way and Andromeda is like about like 20, this is why lambda is changing like the mass of changing like the motion of Milky Way and Andromeda. Any questions? So I found also like analytical solutions, but I'm going like to continue like further. I mean, yes, I mean there are some analytical solutions, but I mean let's go now like to the practical values that we have from Milky Way and Andromeda. So I wanted like to use in the first instance like only the timing argument. So it means with lambda or without lambda. So my prior was the separation, the radial velocity, the tangential velocity, and the cosmological constant. And then I try like to calculate the semi-major axis, eccentricity, and so on and so on. and also like to find what is going to be the small lambda, this kind of like the correction for the local group. And here from full MCMC simulation, I got like this about 10%. So again, the theoretical prediction, the theoretical explanation why the cosmological constant is so important in our in this system. Okay. But now, okay. Now, the problem with this kind of assumption, like the problem with this kind of like timing argument is it's only assumed that these two galaxies are separated for most of the history. And I cannot really know if this is actually correct, right? We're speaking about like two galaxies. I mean, there is a lot of dark matter inside. There is a lot of like maybe interaction, smaller galaxies, and so on and so on. So we included like simulations of galaxy pairs. So it means like you have a catalog of many, many galaxy pairs from the simulation. And then you can see from the simulation what is the correct mass. So you get from the simulation also like pairs that includes different velocities, but also like the correct mass. So using this kind of like the calibration from simulation, we could modify the mass of Milky Way and Andromeda. Okay, so we call this kind of like correction factor cosmic bias. Okay, and in the first paper, let me show this. Me and my colleagues from the University of Cambridge and also from the States, by the simulations by Odelia and Luis. So we infer the local group mass. Okay, so we had like the tangential velocity, we calculate the mass by the timing argument, and then we corrected this by the simulations. So eventually, we found that the total mass of Milky Way and Andromeda is about like 3, 10 to the power of 12 solar masses with big error inside. But just like to remind you, the mass of Milky Way is more or less 1 independently, right? I mean, if you have like flat rotation curves of galaxies and so on, you can calculate more or less like the Milky Way mass, which is about like 10 to the power of 12 solar masses. And the mass of Andromeda more or less is about like 2 10 to the power of 12 solar masses. So this is actually show that kind of like our assumption they were like separated for most of the history of the universe is a valid assumption. And there are like other papers that try like to cite like this original paper that they're try like to claim the same thing. Okay, that like to conclude the same thing, that most of the history of the universe, these two galaxies are separated. Any questions so far? Okay, now let's okay, I'll skip this. Now, I want to show you on the other way around. How can I derive an upper bound on the cosmological constant based on the knowledge that we have on Milky Way and Andromeda? Because in one side, the cosmological constant creates like some repulsion force, right? If like the repulsion force is like stronger, I need larger mass to finish like in the same separation, at the same velocities, and so on and so on. So in this plot, this is what you can see like here. I try to calculate using the simulations and the whole calibration, okay, what is going to be the predicted mass of Milky Way and Andromeda, but for different values of the cosmological constant. So it means like my repulsion force can be like larger, even like 2 times, 3 times, 4 times, and so on. And then obviously you can see that if you have stronger repulsion force, in order like to finish in the same separation, I have to have larger mass. So this is kind of like the dependence that you see here in blue with the error. Now, on the other hand, we have independent estimation for the local group mass, which is from the mass of Milky Way plus the mass of Andromeda. We have an assumption here. So this is kind of like the mass that you see like in red. So if I have like these two estimations, I can infer some upper bound on lambda, okay, by using like Bayesian analysis to define like a chi-square and so on. So this is what you can see on the left panel, on the right panel here, okay? This is the chi-square that emerged from the mass, okay? And you see that all of the possible values up to like about 5, right? I mean, this is like kind of like the upper bound. the cosmological constant can be, because of the big errors of the tangential velocity or the cosmic bias, the cosmological constant can have any value from 0 up to 5, about 5. So you get like overfit. But if the cosmological constant is going to be larger than this, the mass is going to be like too large. And it doesn't make sense from the astronomy that we know about the local group. Okay? So based on this, this is kind of like the result that you got from the Bayesian analysis, 3 ± 2. So the upper bound is about like 5 lambda. 5 like the values from Planck. So it means only based on the local group dynamics, we can give like some upper bound on the cosmological constant, which is very close to the value that we know of lambda. Now, we also try like to use like future measurements. So it means like in future measurements, we said, let's say that we know very accurately what is going to be the tangential velocity. So these are like the error of the tangential velocity, the radial velocity, and the separation are very low. But then lower error for the tangential velocity. And also the cosmic bias, it's going to be increased by like better simulations. And then we made like upper bound, which is even better. So in some way, it's like 1.6 plus minus 0.8. So it means kind of like you have a detection, but I mean, not obviously not as good as Planck. Okay. So in our prediction, it's kind of like the local group upper bound is about like 5. And in future is going to be up to 2. But I mean, to detect purely the cosmological constant is going to be like the best thing, but the errors are not going to be as good as Planck value. This is like what you can see in the Gaussian here. Any questions so far? Okay. So it is possible like to constrain correspondingly modified gravity. So it means that instead, like, you know the mass, okay? You know lambda value, but now you try like to say, okay, how much the dynamical Newtonian constant could be? What is the deviation from the Newtonian constant? And the constraint that we got, it was like about 10 to the power of minus 1, which, okay, it's not very tight, okay? I mean, because like the best constraint that we have like on dynamical G is from Cassini satellite, and which is about like 10 to the power of minus 5, okay? So it's kind of like to say, I mean, it's more sensitive to the cosmological constant value, but it's going to be less sensitive for modified gravity theories, like in general, if you have like other theories of gravity, and then you try like to constrain only based on Andromeda system, okay? Yes. So here I made like some other theories, but I mean, more or less like the same prediction. So let me summarize. I mean, first of all, I mean, it's not written here, but I won't like to remind this is, again, the cosmological constant can interrupt or can be like a very meaningful repulsion force only if in your system you have a very large period, which is about like the age of the universe. This is kind of like a very important statement, and I didn't see it like in any other paper. So I mean, this is why I'm like repeating this kind of like statement. So Milky Way and Andromeda is about 17, which is like 30% from this critical value of lambda. So this is why it's highly sensitive to the cosmological constant. And based on this, I can give also like upper bound on lambda, because this is kind of acting as a repulsion force. So I cannot have like too large lambda, because then I will have like too large mass, which it doesn't make sense. So in the future papers that we want like to do, this is kind of like searching. I mean, we're still working on this like in the local void other binaries of galaxies, and based on this, potentially to constrain the cosmological constant from other binary galaxy system. So and I think this is kind of like opening a new gate, like how to have an interaction in between astronomers, which is like, you know, mostly the local universe, and also like cosmologists, so in much further scales. Because if the cosmological constant is what we understand, it has to act as a repulsion force. But if this is not, and this is potentially has like a different form, maybe it could be even 0 in the local universe. Okay, I mean, in the local measurements, it could be even 0. And then I don't know to tell you if I actually answer this question. Do we really measure the cosmological constant? I have no idea. Okay, because it could be even 0 in that sense. And I'm not ruling out Planck, but what I'm saying that this is kind of like on a very large scales. On smaller scales, nobody tested before. So I'll finish like in that question, and I hope everything was clear. So, and sorry for the interruption. So any questions I would love to hear, of the discussion if there is right now. So
thank you very much. Thank you. Indeed. Maybe there are professional questions. So Jonathan Loveday, please. And then Jean Coda.
Hello, thanks for the very nice talk. You mentioned improvements you might achieve with future measurements of our local group. I wondered if you think there's much scope in improving these constraints by looking at other local group type systems.
So this is one from the directions that we're like really careful like thinking about, because in some way, I mean, we have like few candidates. I mean, for instance, like Centaurus and M37, I think this is kind of like a system which is like very similar to the local group. But then the problem that you have with these kind of systems, you don't have the measurement of the tangential velocity. So this is why it needs like to have or simulations to calibrate like this kind of VT, or to integrate over if you have like a lot of galaxies. So these are like two options that we try like to answer. But I mean, this is like the main issue like in this method. But it's supposed to be like something new, something novel. Okay.
Great, thanks. And one other quick question is, some of your slides had units of GYS. Could you say what those are? I think it was when you're discussing relative periods, you had the GYS in the denominator.
GYS, gigayears?
Yes, there we are, yes.
So, yes. So, I mean, if you take from the cosmological constant value purely, like lambda, even just like go to you know, like one from the papers, what is lambda value? But then you try like to convert, because lambda has dimensions of 1/meter square, okay? And if you calculate from this the corresponding period, so you get 60, about 60.
So those units are gigayears, are they?
Yes. So the edge of the universe,
yeah.
30.7 gigayears.
Yeah, so I just get confused because I think normally people just use GYR for gigayears, so they're confused by the.
Okay.
That's all. Okay, thanks.
Thank you.
So, Yin Kwada, you have...
Yes, so I think this is probably a very novice question, but I just want, so the equation you showed, the equation of motion with lambda you showed is the equation for acceleration, but we have just a measurement of velocity of Benisty 31. Why can we constrain lambda when we don't know the acceleration?
I mean, I'm trying to understand. So, I mean, in this kind of method, I mean, I just like say that, let's say that I don't know what is the lambda value, okay? But it going to act as a repulsion force, right? I mean, yes, like here. So this is like kind of like attracting, and this is kind of like a repulsion. Now, I tried like to infer the mass based on the method. I mean, based on the calibration from the simulations and everything. And then I've shown like this kind of like correlation. I mean, this is like the key plot, I would say. So if you have like stronger repulsion force, you need to have stronger mass, which is attractive force, okay? But then the mass cannot be like any value because we know the mass of the local group from other estimations, right? I mean, so we know this is kind of like about like 3 up to 4. So this is why you can give, based on this kind of like relation, the upper bound of lambda.
Yeah,
Is this answering your question?
But the force, when you say force, you are talking about acceleration, right? But we don't know the acceleration. We don't have the measurement of acceleration. We know the velocity, but we don't know the acceleration. So I still don't understand why the observation can constrain the acceleration over lambda.
No, because you can infer also the velocities versus like the, I mean, also you can infer, you have the tangential velocity and the radial velocity, right? So they include inside like their equations also like the semi-major axis, the mass, and so on and so on. So you get like 4 equations basically: the time, like the edge of the universe, the separation, the tangential velocity, and the radial velocity. So you get like 4 equations. And from this, you can infer the mass, the semi-major axis, the eccentricity, and the period. Okay, so this is kind of like corresponding to each other. And this is only using like the velocities which are corresponding to the acceleration equations.
So are you basically saying that the orbit is assumed? The shape of the orbit is assumed, and if you know the velocity, then we can infer the acceleration? Okay.
Yes.
I see.
Exactly.
I mean, that sounds like a very big assumption.
Assume here like a binary motion, like a two-body problem.
Okay.
So this is why I said that I used also like calibration from simulations. So it means that you infer the mass by the analytical solution or the numerical solution, but then you have like a lot of pairs of galaxies. They have themselves velocity, separation, and the correct mass. And then you are asking, okay, these kind of like values, these velocities and the mass, where can I find like the corresponding value in the simulations, like in the galaxy pairs from the simulations? So then we get what's called the cosmic bias, which is kind of like a correction factor, which is about like 0.6. Okay. So exactly because of that reason, we have like to correct this by the calibration from simulations. Okay. So the distribution is here. Okay. So this is how the correction factor looks like. So the mass has like some correction inside. Okay. Thank you. I hope this is answering.
Yeah, that's good. Thank you.
I have a naive question about the galaxy evolution. That in the time scale of billions of years, Milky Way and M31 should have evolved. But does this affect the discussion? Affect your discussion?
It's a very good question. I mean, I'll tell you. I mean, in one side, for most of the history of the universe, I don't remember like the correct numbers because there are like few new papers that also try like to say whenever this is like correct. I mean, I think from 5 billion years after the Big Bang up to like now, something like this. This is more or less like a proper assumption. And then like more or less they have almost the same mass, the same period, the same as a two-body system, as a proper two-body system. To tell you the timing argument is correct, fully not, because this is why I use like this kind of assumption. But from what I've seen like now, also like papers like that emerge like after like this paper. So I mean they try like to test this kind of like assumption. For most of the history of the universe, these galaxies are separated enough, and then they have obviously like evolution, but it's not changing by much the whole values. I mean, they wouldn't change like lambda, the upper bound on lambda to be 15. Okay, so okay, but this is a proper effect. Yes, definitely.
Okay.
Thank you.
Sometimes theoreticians propose some experiments to test theory. Do you have some proposal?
I think like to test the theory. I mean, this is kind of like the theory is more or less known. I mean, like if we know
to test by experiment, I have in mind.
Oh, yeah. Oh, I mean, if this is possible, like to test by experiment. My host from Cambridge, Anne Davis, which I collaborated with her like in this work as well. She have done like some work like a year ago or 2 years ago. It was like about from xenon experiment. So they claimed that actually one from the detection was like about some dynamical dark energy, not like a standard model of lambda. In general, but apparently this kind of like detection that they had, this is only from some effect like inside the experiment and not like really some lambda inside. From what I can say, that it seems to me that because like the critical period of lambda is about 60 gigayears, so we have to have a binary system, if we're speaking about like binary systems, binary galaxies or something like that, where they have like a large period, enough large period. So, I mean, if they have like a period of 20 gigayears, something like that, and then it's possible like to calibrate some upper bound on lambda. I don't know if to say like to detect lambda. Okay, so it's kind of like, but in my opinion, this is kind of like a new method which is possible like to go further. Yes, using binary galaxies or binary, I don't know if binary black holes, but I mean they have like to be really separated, so I don't know, but yes. Yes, so this is kind of like the.
So thank you very much for sharing your theory, your experience, and we wish you all the best in your future investigations. So thank you very much.
Thank you very much, and it was very nice to see all of you and to meet all of you. Thank you very much.
Oh.